Welcome to AMETEK Process Instruments educational webinar today on process moisture fundamentals and analysis. I'll be your host today. My name is John Kearney, and I'm the business manager for natural gas for AMETEK PI. Just before we get started, a few ground rules. We are recording the session to share with all attendees following the call, so that will be shared. Please make sure you mute your phone or computer to minimize the background noise for the other attendees on the call. And if you look down on the bottom of your screen, there'll be a call out box there. That's the chat box on Microsoft Teams. I'd encourage you to submit any questions through the chat window, and we'll be glad to answer those at any point during the talk today, and hopefully run a few poll questions as well. So again, welcome, and we'll go ahead and get started. Today we're going to cover impacts of moisture content and water vapor in a variety of process and industrial processes. We're going to talk a little bit about what makes the water molecule so unique, and why does it behave the way it does, and why does it make it somewhat of a difficult molecule to measure in process measurements. We'll cover a number of different fundamentals of measurements. This will be more a terms and definitions section where we go through some basic terminology of key items of moisture measurement, and then we'll try to apply those in some practical examples to get a much better understanding of that. And then I'm going to cover several, but not all, of the important technologies or the common technologies for moisture measurement in industrial processes. Unfortunately, due to the limitation on time that we have today, I won't be able to get through all of them, but we will touch on 3 or 4. And then finally, just at the back of the presentation, we'll briefly cover some of the considerations around sample conditioning. This topic in and of itself can be is an entire webinar series as well, but I'd like to just point out a few at least recommended best practices when it comes to sample conditioning as it relates to moisture measurement. So we'll try to touch on that at the end of the session. So if we jump right in, water is definitely the most abundant molecule on Earth, and as you can see in the slide, I have that, but I also have a but, which we'll talk about in a minute. But water has some interesting properties. It's the only substance that really occurs naturally as a solid, a liquid, and a gas. And unlike most things that freeze, when they freeze, they contract or shrink. Water actually expands by 9% when it freezes, and that's due to some unique properties that we'll talk about in a minute. Just as sort of a light note, I learned that it takes about 20 gallons of water to make 1 pint of beer. So some interesting facts there about water. But one of the unique things about water is it's what's called a polar molecule. And what a polar molecule is a molecule that has a weak partial negative charge on one end of the molecule, and a partial positive charge or region on the other end of the molecule. And that's what makes up a polar molecule. Water has that, and we'll talk a little bit more detail in a few minutes on why that is. But the polarity of water causes it to form what's called hydrogen bonds. And what a hydrogen bond is the negative side of one water molecule is attracted to the positive side of another molecule, and it makes these loose linkages between water molecules themselves. And we'll talk a little bit more about that in a couple of slides. But one thing hydrogen bonding does, it gives water some unique properties. Probably the most similar molecule to water is hydrogen sulfide, H2S. They're very comparable molecules, but they have some very different properties, all of which is really around hydrogen bonding. Hydrogen sulfide does not have significant hydrogen bonding, and that's primarily due to the fact that the sulfur molecule has a very low electron negativity, whereas oxygen has a very high electron negativity. So water boils at 100 degrees C, but hydrogen sulfide boils somewhere near negative 60 degrees C. So a very big difference in boiling points between two similar molecules. Additionally, hydrogen bonding gives water some unique surface tension properties. Surface tension is basically the attraction of molecules to adhere to each other or to a surface. And hydrogen bonding allows water molecules to sort of stick or absorb to surfaces. And I want you to keep that in mind as we get further into the presentation. We'll talk a bit about that absorption and what how that manifests itself in the measurement and the behavior of water in industrial processes. And then the last sort of unique property that hydrogen bonding provides is around the heat capacity. And what heat capacity really is the ability of a molecule to hold heat in. And water has a very high heat capacity. It takes a lot of energy to boil water, and it can hold a lot of heat or energy within water. And that's all due to the hydrogen bonding, the fact that you have to break the hydrogen bonds before you can even start to boil off water. So it has a very high heat capacity as well. So those are some interesting facts. But the polarity in hydrogen bonding, you'll see as we talk further into the presentation, are really what drives some of the unique behavior that we see when we try to measure and analyze water in industrial processes. Water or water vapor or moisture content is not something that most processes want. And unfortunately, what we have is the processes have very low moisture, and ambient air, no matter where you are in the world, has quite a bit of moisture content in it. So we're always battling that fact that we could have leaks of water vapor into our process and so on. Some of the things water can do is, as you know, especially for folks that live in colder climates, water freezes. And as I mentioned a few minutes ago, water expands when it freezes. So if you have water in a process piping or in some other pump or other mechanical device, and water's in there and it freezes, it will expand, and that can cause certainly damage to any of the infrastructure that you have. In natural gas, water with methane can form what's called hydrates, which is essentially methane ice. There's a picture on the right-hand side of two folks removing a large amount of methane ice or hydrate from a pipe. You can obviously see that would prevent flow of natural gas in a pipeline, which would be a big problem for the natural gas folks. And then obviously water or water vapor can cause rust. So certainly can damage any steel pipes, and it does act as a solvent with lubricants, particularly in compressed air or dry air systems. So it's really not wanted there. Water, when in the presence of other compounds, for example, H2S or chlorine or carbon dioxide, can form acids such as sulfuric acid or hydrochloric acid that obviously would then corrode any mechanical infrastructure that you might have, could damage the analyzers and so on. So it does promote the formation of those sort of non-desired acids. Within natural gas, water vapor impacts the heating value or the BTU content of natural gas. How well does it heat? In the downstream space, such as in refining or petrochemical space, catalysts are typically used as part of the reaction vessels to produce different types of end products. And the catalysts are typically made up of very high-priced metals, platinum as an example. And water, if it's in that process and the feedstocks going into the reactor, can damage the catalyst itself, which is an expensive problem. But water can also reduce the reaction yield that you have and end up producing less of the desired end product. So it affects reaction yields and so on. In the steel industry, particularly in the heat treating space where we're doing annealing or brazing, the presence of water in that process promotes oxidation, which can weaken the steel and not have it be as strong as it should, or cause other problems with the final finish of the end product that folks are trying to make in the steel industry. So water's a problem there. In the semiconductor space, they typically use very ultra high purity gases. In this space, they're typically measuring very low moisture levels, and moisture is a contaminant in those high purity gases and can ultimately affect the production of semiconductor chips and wafers that are used. And then finally, even in the power industry, there's a process whereby the power generation equipment will use something called a hydrogen cooled generator, which is part of the process to make power. And if water is within that process, there can be a bit of arcing that's caused that can really do some damage. So even in the power industry, water is a problem. So you can see water shows up in a real wide range of processes and really not desired in any of them. So it's important for us to measure and control the water vapor and the moisture content in our process. So I mentioned a few minutes ago about some unique properties of water being polarity and hydrogen bonding. So let's just talk a little bit more detail about that. So water, as most people know, is formed with 2 hydrogen and 1 oxygen atom. And together they form the water molecule. What happens within the water molecule is oxygen, because of its strong electron negativity, will pull the electrons away from the hydrogen and towards the oxygen atom. And what that sets up in the molecule is a partial negative charge region around the oxygen molecule and a partial positively charged region around the hydrogen molecules. What that allows water to do is bond with itself through this process called hydrogen bonding, where the negative oxygen on one water molecule will bond with a positive hydrogen area on the other water molecule. And in fact, for any given water molecule, it can form hydrogen bonds with up to 4 other molecules. So it can do quite a bit of hydrogen bonding itself. These are all weak linkages, but what hydrogen bonding does is it allows water to absorb or stick to surfaces, which manifests itself when we start to talk about response time and the ability to remove water and things like that. And it can impact some of the technologies as well and how they work. So it's important to understand that this is an inherent property of water and something that we just have to account for when we're trying to measure and analyze water and when we're trying to build and design our sample conditioning systems and sample transport systems. So I started a number of years ago in the world of moisture measurement, and I came in probably like most people as a fairly inexperienced person and somebody that really only heard about maybe water or water vapor type terms, maybe from watching the weather, reading the weather, things like dew point or relative humidity that you might see on the weather. So there is a lot of confusion and uncertainty around what is water, what is the water content, how do you measure it? And this is part of the issue we have in the industry where there's just a lot of confusion among users. Some of it's different specifications, both from how a plant or a design may be written. It's also confusing with different manufacturer specs and how those are written and how the different technologies express their capability. So it does cause a lot of bit of confusion in the industry. The other thing is, unlike other analyzer analytical techniques, it's hard to validate moisture readings and moisture analyzers in the field. You know, it's not as easy to calibrate a moisture analyzer as it is to maybe calibrate an oxygen analyzer. For those that work with mass spectrometers or gas chromatographs, you know, you can do calibrations in the field with cylinder blends and so on. It's difficult to do that with most of the moisture technologies and how water behaves. So that also lends itself to, I think, a little bit of uncertainty. And then, which hopefully we'll correct today and shed some light on, is just conflicting readings between different moisture analyzers, different moisture sensor technologies, and so on. So we'll try to go through that in a little detail and hopefully clear up some of that and be able to have folks better understand how that all works. So my goal for today is really just to try to get us to talk the same language when it comes to moisture measurement and try to understand how these various terms on the slide, dew point and ppm and so on, all relate to each other and how they really kind of behave in a real world example. And we'll talk about that as in the next few slides. So the way I think about water content measurements or moisture measurements is really 2 different ways. One is physical state, where the water vapor is changing, physically changing, say from a gas to a liquid or a liquid to a solid. And the other is what I just think of as moisture content or number of water molecules, what we call abundance of water measurements. These are things like parts per million by weight in a liquid or gas, parts per million by volume in a gas. In the natural gas industry, they use a sort of specific terminology for them, which might be grams per cubic meter or pounds of water per million standard cubic feet. These are all just terminology that folks use to express moisture content in their process. There's also other terms like relative humidity, et cetera, that can be used as well. So the way I try to think about that is those kind of 2 different things. One is dew frost point, which is measuring a physical state change, and then the others are sort of counting the water molecules in the process. So let's at least start first with the physical state measurements. And we'll go through some sort of basic terms here the next couple of slides, just to get us all grounded on what we're talking about. Vapor pressure water, the way I think about it, is really the partial pressure that water molecules exert in the system. So if you think of yourself as a water molecule, I tend to think of, okay, what's the pressure or the force that I'm exerting on my own in a system? The scientific or engineering definition is kind of at the first bullet. It's basically the pressure at which water vapor is in thermodynamic equilibrium with the condensed state. The thing to know about vapor pressure of water is it's determined experimentally. There's a number of different equations that can be used to calculate water vapor pressure. I've listed 5 of them here on the slide: Buck, Goff-Gratch, Tettens, Clausius-Clapeyron, et cetera. I'm happy after the session, if anybody wants to reach out and contact me, you go into any of those in detail or provide you with some sort of references to get that information. I put a couple of example equations up here on the slide. The other way you can look at it is the equations basically fill out a lookup table, if you will, that relates vapor pressure water to temperature. So vapor pressure water is something that's experimentally determined and defined. The other term we just want to touch on is saturation vapor pressure. This is basically the pressure that's established when liquid water or ice is present and the gas cannot hold any more water molecules in it. So if you look at the graphic on the bottom, it's essentially as you move from left to right, you get closer and closer to saturation, ultimately to saturation on the picture on the far right. When we're at saturation, the evaporation rate and the condensation rate are equal. And the important takeaway really on saturation vapor pressure is it's determined by temperature. And the way I think about this practically is in the summer months, we feel more uncomfortable because it gets more humid. Why does it get more humid? Well, the air temperature is much higher, so it can hold more and more water vapor in it, and we feel more and more uncomfortable as a result. But the higher the temperature of the gas, the more water it can hold. The lower the temperature of the gas, the less water it can hold from a vapor pressure perspective. So that's a good way to think about saturation vapor pressure. The other term you'll hear is dew point temperature, and this is fundamentally, the temperature when a gas is cool, where the first molecule of water vapor begins to condense out as liquid water. And I have a small cartoon there. You can see at the bottom it says dew point is 51 degrees C, and as the temperature comes down from 53 to 51, you can see the little water molecules start to come out. The thing on dew point temperature is that for any given partial pressure of water or vapor pressure, there's only one dew point temperature. So they're equated to one another, and dew point is completely temperature independent. So it doesn't matter if it's hot or cold. The dew point temperature of a gas is defined by the partial pressure or vapor pressure of water in the gas. And that's an important thing to understand. And we'll talk a little bit more about that in the practical example coming up. The other term you might hear is something called frost point temperature. And really the only difference between this and dew point temperature is as the gas is cooled, this is a temperature where the first molecule of water vapor begins to come out. Instead of as a liquid, it comes out as a solid, and it's ice. So that's frost point temperature. And just like dew point, for any given partial pressure or vapor pressure of water, there's only one frost point temperature. One thing to note is most moisture analyzers in the industry report frost point temperature under 0 degrees C and dew point temperature above 0 degrees C. The one exception to that is chilled mirrors technology or chilled mirror sensors. They can actually report both dew point and frost point below 0 C. I'm not going to go into that nuance today, but happy to speak with anybody after the webinar if you'd like more information on that. But know that a lot of us talk and refer to dew point below 0 C, but typically that's actually really frost point, and that's what most analyzers are measuring fundamentally at those temperatures. Everything we're going to talk about today is going to be based on the ideal gas law. I'm not going to talk about systems that have some variance to the ideal gas law, which would most notably be natural gas or high pressure carbon dioxide. So just know the assumption, everything that we're going to talk about from this point forward will be based on the ideal gas law. The other thing we should just touch on briefly is a law called Dalton's law of partial pressure. This gentleman named Dalton discovered this and had a law named after him. But what Dalton discovered was that the total pressure of a system is comprised of the sum of all the individual partial pressures of each component that make up that system. And this is an important principle to understand as we talk about how does pressure impact dew point and ppm and moisture content, and how does pressure impact the reading of moisture that we're trying to do. So keep in mind Dalton's law of partial pressure, and maybe let's just consider an example to kind of better understand this a little better. So if we talk about air, air has a number of components in it. So what would be the pressure pressures of air? Well, first of all, air is made up of nitrogen, oxygen, carbon dioxide, water vapor, and then usually some small amount of inerts make up air. So air has a composition to it that I think most people are familiar with. It's typically 78 or 79% oxygen. Nitrogen, 20 or 21% oxygen. Then it'll have very small amounts of carbon dioxide, inert gases, and water vapor. So if we take a look at air at 1 atmosphere, what would that look like from Dalton's law of partial pressure? Well, 1 atmosphere of air in this case would be made up of 0.78 atmospheres of nitrogen using the pie chart shown, 0.2 atmospheres of oxygen, 0.003 atmospheres of CO2, 0.01 atmospheres of water at 1%, and then 0.0097 atmospheres of the inerts in this simple example that we have. So those are all the individual partial pressures of air that make up a 1 atmosphere air sample, if you will. Let's start to try to tie all this together in a sort of a scenario around moisture. So if we look at a system, let's just consider it's compressed air. it's 100 psig pressure in the system, and I've just said that we have 0.015 psia as the vapor pressure of water in the system. We'll just establish that. And let's consider a scenario where we increase the system pressure up to 1,000 psig. So we've gone from 100 to 1,000. And the question is, does the vapor pressure of water increase? Does it decrease, or does it remain constant? And we're going to open up a poll question in the chat window for folks to answer, and appreciate if you also want to just make a comment or anything in the chat box. I'll just give a few seconds here for folks to just quickly weigh in, and we're getting a couple different answers here, so that's good. So if we go back to this example, what really happens is water vapor pressure increases as we increase the total pressure of the system. So let's go through that and understand why. It's all around Dalton's law of partial pressure. As we raise the total pressure of the system from 100 to 1,000, we're raising the partial pressure of all the components in the air system. So the nitrogen, the oxygen, the CO2, the water vapor, and the inerts. So in this case, water vapor increases from 0.015 to 0.113 psia, and that's all the result of Dalton's law of partial pressure. So we've increased total pressure, we've increased vapor pressure of water. So now let's take it a step further with the terminology, and let's now add in due frost point temperature. So we'll again set the system the same way, 100 psig, 0.015 psia is the vapor pressure of water. If you used one of the equations I mentioned a few slides ago, or used the lookup table, you would find out that 0.015 psia equates to a frost point temperature of minus 20 degrees C. So again, we're going to raise the system pressure, total system pressure, to 1,000. We'll raise the vapor pressure of water to 0.133. And the question is, would the frost point temperature be greater than minus 20 C, less than minus 20 C, or equal to minus 20 C? And again, we'll open up a poll question on the chat window, and appreciate if you do that or comment in the chat. And we have a few folks weighing in on the chat that are all correct, which is good to see. What happens to frost point in this example is it ends up being greater than minus 20 degrees C. So why is that? Well, we raised the vapor pressure of water from 0.015 psia to 0.133 psia. So as a result, the frost point's actually gone from minus 20 C up to 5.7 degrees C. So total pressure increased. We increased vapor pressure of water, and now we've increased due frost point temperature, which is somewhat interesting. So if you were looking at this practically, you might be measuring moisture before and after, let's say, a gas compressor. And if we assume there's no leaks in the compressor, if you were comparing two moisture analyzers, and the moisture analyzer before the compressor was reading minus 20, an analyzer after the compressor was reading plus 5.7 C, the two analyzers would actually be in agreement, even though the values themselves look different. If both were reading the same value, let's say both were reading minus 20 C, then you would definitely have a problem with the moisture measurement point that was at 1,000 psig, because we wouldn't expect that. So here's a good example of where, understanding the terminology and also understanding how pressure impacts this can help troubleshoot or figure out whether or not your analyzer actually agreeing with one another or not. So if we take it a step further, let's just talk quickly about what abundance of water measurements are, and we'll come back to that example here momentarily. But like I said earlier, the way I think about abundance of water measurements is basically just how much water is in the system. We're effectively counting the water molecules in the system. And the common terms, just to reiterate, parts per million by weight, which is typically used in liquids, but also can be used in gases. A very common measurement for gases, however, is parts per million by volume. Many industries use that as the language in which they speak of when they talk about moisture content. And then, as I mentioned earlier, some of the industries have some special terminology like natural gas with grams per cubic meter or pounds per million standard cubic feet. And then there's other absolute humidity measurements. So let's revisit our example from earlier. If we had 100 psig air, again, at minus 20 C frost point, the ppm value, actually, if you ran the calculation, would be just under 131 ppm. And the question now is, if we increase the system pressure, again, to 1,000, and we said earlier we would raise our vapor pressure of water by Dalton's law of partial pressure to 0.133. If we did the calculation, we'd find out that was a dew point of plus 5.7 degrees C. So the question is, does the ppm value increase, decrease, or remain the same? And we'll open up a chat again window with our poll question, and just curious on that as well. You can comment in on the chat itself, and we're getting some commentary there, which is great. And what happens on ppm actually is that it remains the same, and that surprises some people, I think, on occasion. But we've changed the pressure, we've changed the vapor pressure of water, which is all Dalton's law of partial pressure, and we've changed the frost point, dew point by different numbers. But ppm, because we're actually counting water molecules, we didn't add or subtract any water from the system. We didn't say insert a syringe and squeeze more water in, and we also didn't use a dryer or anything to take more water molecules out. And just interesting enough, on the graphic that I happen to get, if you were to imagine these bubbles that are shown here on the right side as water molecules, you would find out that there's 10 on the top one and 10 on the bottom, and we haven't added or subtracted any water from the system, or added any water to the system either way. So the moisture content itself would remain the same. So now we'll just switch gears maybe and talk a little bit about the moisture sensor technologies. And the common technologies, I listed 7 here, the more common moisture measurement technologies. With respect to any of the technologies, the way I think about moisture measurement and approach it is I start with the user application and then take a look at the application requirements, which can be things like what's the measurement range that somebody has, what kind of accuracy are they looking for, is response time a significant concern for the process and what they're trying to measure, how much is it going to cost to do the measurement, is the background gas constant, what's in the background gas, any contaminants that might impact the sensor technology. Those are all kind of sensor related items. And then you get into things that have to do pretty more like with the analyzer, the package around hazardous area, environmental temperature or things of that sort, power, etc. So there, I listed down here 7 common moisture technologies: stain tubes, impedance sensors, Fabry-Perot light technology, electrolytic, chill mirror, quartz crystal microbalance, and finally the newest entrant, I guess, into the space of moisture measurement, tunable diode laser absorption spectroscopy, or TDLAS. Just in the interest of time, because we only have a little less than an hour to talk, I'm just going to touch on 4 of the technologies today, talk a little bit about how they work, and a little bit of some of the strengths of the technology, and then not so much disadvantages, but just things you want to be aware of or think about, and ask some questions around if you're going to decide to use one of these technologies, and some of what maybe their limitations are. So we'll just go through these briefly and talk a little bit through that. So impedance-based sensors, sometimes referred to as capacitance sensors as well, can be P2O5, could be aluminum oxide, silicon oxide. There's a number of different impedance type technologies here. But typically there's an oxide layer that's in the middle of 2 metal layers. The bottom layer is usually a hard metal, and then the top layer is some kind of permeable metal layer that allows the water molecules to adsorb and desorb. The picture on the top right kind of depicts all the pores of the oxide layer to be the same diameter, the same height, the same width apart, and that can be true in some, but the more common way to think about it, or the way I think about it, is imagine a bowl of spaghetti. The bottom of the bowl is your lower electrode, or your bottom layer. The spaghetti itself is the measuring layer, the oxide layer, and then if you put a meatball on top of your spaghetti, that's your permeable upper gold layer or metal layer that you have there. And the way these sensor technologies work is the water molecules adsorb and desorb along those pore walls that you see here on the slide, and they adsorb and desorb on the sides of the pore walls, and that changes the impedance signal that comes from the sensor itself. So you can imagine a wire connected to the bottom of your bowl, a wire connected to your meatball, and we're measuring the impedance or capacitance that comes from that sensor technology. Typically, they're calibrated with impedance versus dew point or frost point, and that's how they're calibrated. So they typically measure dew and frost point temperature. They're very commonly used across a wide array of industries. Some of the advantages that this type of technology has, it does have a very wide operating range. It can measure from lower ppm levels all the way up, approaching tens of thousands even of ppm, near percent levels at times. So very wide operating range. Typically, these sensors are relatively small in size, so they're fairly portable, if you will. You can also mount them remotely from electronics, which is a nice advantage. Impedance sensors can operate at atmospheric pressure, but all the way up to typically line pressures could be thousands of psig. And they're able to operate up at the elevated line pressures. You don't necessarily have to regulate pressure down when you use these types of sensors. And generally speaking, impedance sensors are background gas sensitive. So you can have an impedance sensor and use it in let's say, air or nitrogen gas, for example, and then move it to helium, then move it to natural gas, which is primarily methane. And the sensors themselves are relatively insensitive to changes in the background gas. Some of the things just to keep in mind if you're considering this technology that you might want to just think about or ask on, just to make sure, is I classify these sensors as moderately accurate. They're not as accurate as some of the other technologies out there, but they're also not as broadly accurate as, say, some of stain tubes or relative humidity sensors or things like that that have more of a gross accuracy. So these kind of fit in between there. The sensor response time, which we can talk about for a minute, is fairly slow going from a wet to a dry condition, but fairly fast dry to wet. And a good example, a way to think about this is imagine you're at your kitchen sink and you have to wash the dishes and you purchase a brand new sponge from the store. The sponge, you take it out of the wrapper and it's very dry, sometimes even might be even hard to the press. And if you were to put the sponge immediately under the water, it wets up more or less instantaneously and gets very wet. If I asked you to dry the sponge back to its original condition, that would take a long time. You'd wring the sponge out, squeeze it in your hand, and then you probably have to leave it out, for some period of time to get the rest of the remaining water out, or maybe try to put it in the sun or something to dry it out faster. So that's what happens across not just impedance sensors, but even in the moisture systems themselves. Things can wet up very fast, but tend to be slower when they want to dry out. And a lot of that has to do with what we talked about earlier with water being a polar molecule and its hydrogen bonding. But impedance sensors are good on the wet up side, but they tend to take a little while to dry out. And the way you can think about that, specific to impedance sensors, is just you're trying to remove water molecules from that spaghetti strand of pores, and it just takes time to drive the water back out of those. A couple other things just to keep in mind with impedance sensors. Molecules that look like water and have a large OH or hydroxyl ion on them can be counted as water molecules with impedance sensors. It's not necessarily one-to-one where you have one molecule of this contaminant and it counts as one water, but it has an influence. Some common contaminants, we see them sometimes in natural gas, triethylene glycol or methanol or amines that look chemically similar. Just want to be aware of that. Typically, these sensors are calibrated on some kind of an annual or semi-annual basis with the manufacturers that produce those. So you want to make sure you're up and calibrating those regularly so you have good measurements. And then anything that could, obviously, we have different metals that we're using as part of the sensor construction. So anything that could potentially attack the metal, such as aggressive acids, for example, you want to just be aware of if you have any of those in your process. Quartz crystal microbalance is another common technology. The way this sensor technology works, and I have a few slides to go through on this one, is there's a quartz crystal, which I depicted here in the middle of the photograph, that's coated with a hygroscopic material. And you think of the hygroscopic material as a material that's going to absorb water to it as the process changes. And the way the quartz crystal works is that the quartz itself is oscillating at a certain frequency. And what happens is the water molecules that are in the process will adsorb and desorb off the quartz crystal coating. And that changes the frequency of the quartz crystal as it's oscillating. So the more water that's on the hygroscopic material, the slower the crystal oscillates. The less water that's on the material, the faster the crystal oscillates. So we look at that frequency of oscillation and correlate that to moisture concentration, typically something like ppm or ppb, and that's how these sensors are typically calibrated. I'm going to go through a little more detail in a minute here just on that cycle and so on, but some of the things that the quartz crystal sensor has some strength in, it's very sensitive and fairly accurate. It typically has accuracies, in the low ppm range. And it can have very low detection limits down into the sub 1 and down into the ppb range as well. So it's very good at measuring low moisture content gases. The technology itself is also very fast with this oscillating measurement cycle, which I'll speak of in a minute. And quartz crystal is really one of the only technologies that has a built-in verification system in order to verify the sensor in the field. It's really one of the only ones that can do that. And I'll talk about that in a minute too, just to explain that a little further. Some things you want to be careful with or ask about on quartz crystal sensors. One is it can be susceptible, similar to the impedance sensors, to molecules that look like water. So if you have glycol or methanol, you want to be aware of that and account for it. And then if you're, this is typically for natural gas, but if you're in a high H2S environment, you want to be careful and make sure you have a specially treated cell that can handle that. So we just talked briefly a little bit more about how the technology works. There's actually two crystals in a quartz crystal microbalance sensor. One is the measuring crystal, which is the crystal that is exposed to the process gas. And then there's a sealed reference crystal that isn't exposed to the process gas. So why a reference is used is it provides some inherent compensation for any temperature-induced frequency changes that might be occurring because of ambient temperature differences. So the way the sensor typically works is if you go from the top right, the red line, process gas flows across the measuring sensor, measuring element of quartz crystal, and we see a frequency change because we've now absorbed some water from the wet process gas, if you will. And that reading or that frequency is compared with the reference, the sealed reference. And that usually happens for about 30 seconds. And then the gas is switched and goes through a dryer, and there's now dry gas flowing into the measurement crystal. And that now is going to oscillate at a higher frequency, a little bit higher because there's a little less water now on the hygroscopic material. And that's compared to the reference crystal. And we look at the difference in those frequencies to get a frequency difference, and then that's related to the moisture content in the gas. So every 30 seconds, this sensor goes from sample to reference, reference to sample, and so on and so forth every 30 seconds. Sort of how that flows in the analyzer itself is the sample gas comes in, it flows through the quartz crystal measuring cell and then out in the sample path. In the reference path, it goes through, as I mentioned, the dryer, and then through the sample crystal. So every 30 seconds that's happening. And then if a user had a question on their reading or wanted to verify the moisture analyzer itself, quartz crystal microbalance sensors have built-in moisture generators that are traceable to a laboratory typically, and usually might be a moisture generator that can generate 1 ppm or maybe even 50 ppm. And you can flow the gas through a traceable moisture generator and see if the analyzer reads the value that the moisture generator is supposed to output. And if it does, then obviously it's been verified. If it doesn't, then you can start to do some further diagnosis if you had to. But quartz crystal microbalance, or QCM, is one of the only technologies that has sort of this built-in inherent capability to it. And then last, just talked about the newest entrant, which is TDLAS, or tunable diode laser absorption spectroscopy. In this case, there's a laser diode that's tuned to a specific wavelength, and the wavelength it's tuned to is the wavelength where water molecules will absorb that light energy. So the laser diode emits a laser beam, and the laser beam travels into a sample cell, which is where the process gas is flowing. In this picture, we show just what's called a V-bounce, but just a bounce down to a mirror and a bounce back to the detector. Other absorber cells can have lots of bounces. They're called Harriet cells. They have many bounces in here. And really the fundamental difference is just extending the light path to allow more light to be exposed to the sample gas itself. What happens with TDLAS analyzers is the water molecules in the absorption cell will absorb some of the energy of the light. And then what's measured on the photodiode is basically the amount of energy lost, which is directly correlated to moisture concentration. In some TDLAS analyzers, they also split the beam and send a portion of the beam to what's called a reference cell or a reference ampule. And what the reference cell has is it has a known concentration of the analyte that you're interested in measuring, in this case, water. And what it allows the device to do is stay locked in or on the correct wavelength in order to measure water. So it's basically an optical verification to ensure that the laser system is working correctly. This is like a typical scan. So what happens is that the laser light is being scanned across sort of a narrow wavelength of light. And in this case, we're looking at water vapor, but in this case, it's scanning across. There's 4 peaks here. The dark blue or purplish line is the methane background. There's basically zero water being absorbed there. And you can see the peaks increase with increasing water vapor. In this example, it just goes from 100 up to 500 ppm. But that's what's happening. The laser beam is scanning across this narrow band, and we're picking. These peaks are a depiction of the light energy that's absorbed or lost due to water being in the process. So TDLS analyzers, because we're talking about light, you can think of it as operating at the speed of light. They're very fast both to the wet to dry condition, so and the dry to wet condition. So it does well on an upset, going from dry to wet, but also very well once a process correction has been made and the system starts to dry back down. TDS analyzers are very fast. Because they're tuned to a very narrow wavelength, TDS analyzers are generally immune to any contaminants, unless a contaminant has a absorption wavelength that's exactly the same as, in this case, water. It's really going to be immune to contaminants you might commonly find in processes, whether that's methanol or H2S or whatever it might be. They're very analyte-specific measurement devices. Because only light is touching the process, if you were touching the sample gas, they really have very little maintenance to them, unlike other technologies where the sensor contacts the process. In the case of TDLAS, only light beam is contacting the process. So they usually have moderately, higher capex, but lower opex over the long term. As I mentioned, the laser beam scans across a wavelength, and you can pick and choose which laser you want. And you can actually measure not only water, but with other laser wavelengths, you could measure other analytes, such as, say, CO2 or oxygen or H2S or anything like that. So the technology itself does have the capability to measure other analytes. That doesn't mean necessarily one laser can do all that, but the analyzer technology itself could do that. And then, as I mentioned, some devices have this line locking feature, which is basically a continuous verification of the optical reference cell, where the light beam is locked on to the wavelength for the analyte of interest, and that ensures that in the measurement cell we're at the correct wavelength to make an accurate and reliable measurement. So TDLS offers a number of advantages. A couple of things to just be careful of with TDLS. One is it tends to be sensitive to background gas changes. So if you have a system or a process with a widely varying background gas, TDLS may or may not be able to handle that. And the reason for that is as you change background gases, you may start to introduce contaminant or compounds that may have an influence in the region where you're trying to measure, say in this case, water. So that's one thing. And as a result of that, most manufacturers, when they're considering TDLS, will ask you for your gas composition, and they'll typically calibrate the analyzer in a gas that's somewhat similar to the process gas that you're using. In some cases, it might be identical, but certainly similar to the process gas using, to be sure that that any interferences in the background gas can be accounted for. And then most TDLS analyzers have temperature and pressure compensation, but all these analyzers work at or near atmospheric pressure. So you want to make sure that you have good pressure regulation and are aware of that with TDLS analyzers. Then the last technology, just to touch on briefly, is chill mirror sensors. These really come in two different forms. One is a manual, and the other type is automatic. The principle of operation in either case is the same. Fundamentally, you have a mirror. In the case of a manual device, you're actually looking through an eyepiece at the mirror itself. In the case of the electronic version, you're bouncing a light beam off the mirror to a detector. And what happens on the backside of the mirror is there's some mechanism to cool the mirror temperature. In the case of the manual device, you're using cooling gas, such as CO2 or propane, to cool the temperature of the mirror down. In the case of the automatic version, you're using an electronic cooling mechanism called a Peltier generator to cool the temperature of the mirror down. And literally on a chill mirror device, what happens is as you cool down the mirror, water molecules that are in your gas that you're measuring will begin to drop out as water droplets on the mirror itself. In the case of the manual device, you're going to be looking through the eyepiece and you're going to see dew literally forming on the mirror. In the case of the automatic version, as the dew is formed, the light beam that's bouncing on there will get diffracted and spread apart. And you're reading the temperature at which on the mirror that occurs. In the manual device, you're looking at a thermometer. In the automatic device, the temperature is being measured of the mirror itself electronically. So fundamentally, in a chill mirror device, a mirror is forming dew, and you're measuring the temperature of the mirror when that dew forms. So it's a very accurate device. Most chill mirror sensors are considered primary standards. So many metrology labs, many manufacturers use chill mirror analyzers as part of their calibration system, either as the reference itself or as a verification to a generator system that they may have. The technology can measure not only water dew point, but also hydrocarbon dew point. If you cool the mirror, not only do you condense water out, but you can eventually condense out hydrocarbons as well and measure those. There are industry standards written around chill mirror sensors. ASTM D1142 is one for manual devices. And really, they're very accurate, very sensitive devices that can be used. So you'll see these quite often in labs. The thing we don't see as much of these in the process world all the time because generally you want to have a clean gas. If you have any particulate or contaminant that can get on the mirror itself, that can adversely impact the measurement. In the case of the automatic mirror, it can start to cause the light to diffract before it really forms. In the case of the manual mirror, you start to get dirt on that mirror and it gets hard to see what's happening there. The other limitation on these is usually the range on which they can measure. It fundamentally has to do with how well and how low you can cool the mirror. So there are ways to cool it to lower and lower temperatures. It just gets more expensive and cumbersome to do that. But in the manual devices, you can use different cooling mechanisms to try to drive the mirror temperature down. In the automated devices, it just gets into how many Peltier generators you want to have to lower and lower the temperature, and therefore lower and lower the dew point measurements that you're making. But these are definitely industry standards, and you'll definitely see them in various labs. I want to just touch on a couple things here as we get into sample conditioning. One is sort of this how dry is dry phenomenon. Talked to many users over the years, and one thing I've learned in moisture measurement is that drier is always better. And you can never be too dry. So just to put this in perspective, just let's consider 1 ppm. And if we use time as sort of a universal thing that everyone understands, the question is, how small is 1 minute? Well, 1 minute is 1 ppm of almost 2 years, and 1 second is 1 ppm of almost 12 days. So fairly small as it is. When you get down into the part per billion range, it even gets smaller. 1 minute is 1 ppb of almost 19 centuries, and 1 second is 1 ppb of about 32 years. So a fairly long and extensive way to go. And the question really is, can process really achieve this? And yes, many processes do run at low ppm, or in the case of semiconductor, even in the ppb range, but it is a challenge to get there. And part of that challenge is that the moisture analyzer is only really part of the story. The other part of the story is the measurement system itself, which I tend to break apart into 3 sections: the sample extraction, the sample transport, and the sample conditioning systems. The sample extraction basically has to do with how am I going to get my process gas or liquid out of my system, my pipe, and into the sampling system, where the analyzer or sensor is located. The sample transport is the tubing between the extraction point and wherever your analyzer is located. And then obviously we have a sample conditioning system around the analyzer itself. And this is really where probably 80% of the issues happen in our measurement industry. And the other 20% are with the analyzer or something else. But this is really important to get, no matter how expensive or how precise or accurate an analyzer you may use. It's only going to be as good as the measurement system that it's a part of. So if you have a poorly designed and poorly operated measurement system, you're going to end up having poor measurements, even with a really outstanding, great analyzer or technology. Going back to the beginning of the presentation, we talked about water being a sticky molecule and some of the challenges that possesses or poses for us. One of the things to keep in mind is I don't necessarily endorse any of these tubings, but this is way to think about this as counts. Just think of it as high water at 1 and low water at 0. And you can see this is dry down times of water. And you can see we're talking about minutes to even hours. And this is just with different types of stainless steel tubing, electropolished or coated. If I was to put up, plastic or copper tubing or other things, what you would see would be curves that are flatter and further up to the right and extending out quite a bit longer. So it's a real challenge for us to understand and make sure that we have a proper sample conditioning system to avoid the issue of water stickiness and water absorption, which all relates back to the hydrogen bonding and the polarity that we talked about at the beginning of the presentation. And then last thing, just a few, I guess I'll just say recommended best practices from me on sample conditioning design with respect to moisture measurement. One is you always want to have your analyzer and your sample handling system as close as you can to each other in terms of to the sample takeoff point, excuse me. You don't want to install an analyzer and a sample conditioning system hundreds of feet or miles away from where you're taking off on your sample point. Minimum, if you can, is somewhere between 5 meters and 15 feet would be sort of ideal if you can do that. So try to do that and think about that as you're designing where you might want to put your analyzer relative to where your takeoff point is for your process. The other thing is with the sample tap itself into the process, you generally want to go about 1/3 into the sample pipe itself, or the process pipe itself with the sample tap, to get a representative sample out of the process. You want to stay away from the wall and the wall effects that happen, and you want to be in good, laminar flow area and away from the issues that happen along the pipe walls themselves. Ideally, you want to have a continuous run of tubing from the sample takeoff point to the analyzer itself. And don't want to have a lot of breaks in the tubing and connections and reconnections. All that lends itself to is leakage, potential leak sources, as well as just increasing the surface area, which is going to slow down the response of your measurement system. The other thing I'd recommend is upstream of your analyzer, only put the most important components of the sample conditioning system. So generally, that's a filter to protect the analyzer or sensor, and potentially a pressure regulator to ensure that the analyzer is operating at its specified operating pressures. And then I'd recommend putting anything else you might want to downstream of the analyzer. That might be a simple flow indicator or a flow switch or a pressure gauge or anything like that. I'd mount that downstream of the analyzer itself. And then finally, it's good to use heat trace tubing if you can. A couple of reasons why. One is it promotes the desorption of water off the tubing walls by having that tubing heated. Gives a little bit of energy to the tubing walls, which gives a little bit of energy to the water molecules that are stuck on the inside. And also, if you have potentially in your application, if you potentially have hydrocarbons and you have any heavies, it keeps those from condensing out and causing problems with hydrocarbon condensation. So just some examples of recommended best practices around sample conditioning. I know there's a couple of questions that have come in on the chat. One is why do we recommend the sample rotometer and flow meter installation at the outlet side when it is a dew point analyzer system, and what if the flow meter is installed on the inlet side? Well, the reason I recommend a rotometer is on the downstream side is most moisture analyzers don't need precise flow. They simply need just a flow indication. So it might be 2 to 20 standard cubic feet an hour or 1 to 5 liters per minute or whatever it is. But they just need some flow through them, and they don't need overly precise flow. So you're better off mounting a little rotometer downstream of the analyzer, primarily because it's more leak points and more surface area. I guess a related question to that is, does the rotometer cause any back pressure on the analyzer, which is really an excellent question. There's a couple of different ways you can operate an analyzer. If I was designing just say like a very basic sample system for say compressed air measurements, I might have an inlet valve and a filter. I'd have my analyzer, and then downstream I might have a little pressure regulator and then a little rotometer with a valve on it, or a valve and a rotometer, however I might do that, but some way to control the flow rate. And there's really two ways to operate that system. Then one is to fully open the inlet valve, which would put line pressure at your sensor, and then just crack your outlet valve. So in this case, you're measuring the dew frost point temperature at process pressure, which would be the preferred method to do if you're talking about dew frost point. If you're just measuring moisture content, then you could potentially just slightly crack the inlet valve, but fully open the outlet valve and run the system more closer to atmospheric pressure, and you're measuring moisture content. And as we said in the example earlier, if pressure changes, moisture content doesn't change because we haven't added or subtracted any water molecules to the device itself. Two more questions have come in on the chat. One is, what is the lower detection limit for dew point analyzers? That varies by analyzer technology. Some of the analyzers have, gross lower detection limits. For example, stain tubes might be in the tens or hundreds of ppm. When you get into things like quartz crystal microbalance sensors, you can get down into the low ppm, tenths of a ppm, even down into the ppb area on some quartz crystal microbalances. There's other technologies out there. One is called cavity ring down, which is commonly used in the ultra high purity market. Those devices can measure into the tens to hundreds of parts per trillion level. So LDL, or low detection limit, really depends on the sensor technology itself. One other question on sample conditioning is, how do I minimize the diurnal effect on moisture measurement, which is a really excellent question. The diurnal effect is caused by water content changing as we change ambient temperature. So what happens on the diurnal effect, if you think about a hot area in Saudi Arabia, is we go from very hot during the day to very cool at night. And what we see happen is we see the moisture content change as we go from day to night. During the day, with the sun beating on the process itself, the process tubing and the sample conditioning system, we see water molecules get energy off the tubing walls and desorb into the gas, and we see a rise in the moisture level. And then at night, the sun goes down, the heat goes away, and those water molecules adhere or stick again back on the surface, and we see the moisture content drop. There's no way to eliminate the diurnal effect, but you can minimize the diurnal effect with a couple of the things I already mentioned. One is trying to keep the sample analyzer as close to the sample takeoff point as possible, which minimizes the sample transport tubing. The other thing you can do is use heat trace tubing on your sample transport tubing. That'll keep that tubing at a fairly constant temperature, which will avoid the fluctuations over day to night, or even summer to winter in some parts of the world. And then within the analyzer system itself, you can try to do some things to control the analyzer sensor area temperature by potentially using a cooler or a sunshade, something like that, that will keep the temperature where the analyzer sensor is at a more constant level. The one thing that'll be difficult for you to control is what happens in the process and the process piping and the infrastructure there. If you have larger pipes, it's potential they may be insulated or underground more often and not above ground, but that can vary quite a bit, and that'll be the one area that'll be a little bit harder to control, but you can at least try to control the sample transport and sample conditioning areas of the system. All right, so I appreciate those are some excellent questions that came in on the chat. Finally, just to wrap up, the moisture. Remember, moisture is a polar molecule. It's going to want to stick to surfaces, and it's going to want to adhere to things, and that's really one of the primary causes of what we see with respect to response time and why water sticks to surfaces. The other thing is when you're looking at moisture technologies, you want to compare apples to apples. So you want to make sure that your dew point temperature is different if you have different pressures. You want to make sure your moisture content in ppm is the same. And then you always want to make sure you're looking at that together. When you're picking the sensor technology, remember it's all about the application. So look at, not only cost, but what range do I want? What actions do I need? Is my background gas changing? What are some key contaminants in there? And then remember, no matter what we do on the sensor and the analyzer, it all comes down to the sample conditioning system and itself. So keep in mind some of the best practices I just shared around sample extraction and transport and so on. So my contact information is there. If anyone has any questions or would like to get into discussion afterwards, I'm happy to do that. And again, appreciate everybody joining today's webinar. So thank you very much, and I hope you have a good rest of your day. Thank you.